So we're going to extend area. We know area of a region is just top graph minus bottom graph. But we're going to take that concept and we're going to extend it into volume. Okay, so let me do an example of area again, so we can have something to look at in terms of comparisons and differences with area and volume. So let's say we have a region y equals root x between 0 and 4. And this is the shaded region that we are concerned about. We're just reviewing area for now. And area is just top minus bottom. And we can have one representative rectangle. Ultimately, they're infinitely thin rectangles that extend from one end to the other, but this is the orientation. It's going to be top minus bottom. And the area is just the top graph minus bottom graph. And top graph is the graph that's the upper boundary of the shaded region. And the bottom graph is a lower boundary of the shaded region. So the top one here is y equals root x. And the bottom one here is y equals 0. Right, you have the curve up top, and then you have the x-axis below. So area is a definite integral from 0 to 4. And then the top minus bottom, which is root x minus 0, right? Root x is the top, bottom is 0. This represents the height of the rectangle. Right? And it continually changes because that root x will get higher and higher, which will allow this height of each of the infinitely thin rectangles to continue to grow. Right? So it's a continually changing height of the rectangle. And then the dx represents the width component of your rectangle. So height times width, which we're accumulating all these infinitely thin heights and widths across from 0 to 4. And if we were to work this out here, this ends up integral of 1/2 dx. We go through power rule, plug in upper and lower bound, and this gets us all the way to 16 over 3. And we say units squared because this is an area formula. So this integral notation allows us to add infinite numbers of differently sized rectangles to form the exact area calculation. Okay. Now, this method, this is what we're going to do. We're going to find volume by this method. We're going to set things up the same way, very much the same way, but everything that we're building is is representing something a little different. So with this method, we're going to take this region that we created by f of x in the x-axis. So I purposely made it the same shaded region. Same shaded region, same graph, same boundaries. But rather than just stopping there, we're going to take this shaded region. This is just a two-dimensional shaded region, and we're going to rotate that whole shaded region around an axis. Okay. And our axis is going to be the x-axis here. So we're going to use a dotted line to indicate kind of like the new center of this shape. So it looks like this dotted line is at the edge of the diagram, but it's actually at the center of the diagram because after the rotation occurs, this dotted line will now be in the center of the object. So as the rotation occurs, we're basically creating these circular discs or this circular bowl, right? And the idea is that, well, we can, just like how we can think of this shaded region as the sum of infinitely thin rectangles, we can think of this bowl-shaped object as the sum of infinitely thin areas of circular discs. Okay. So we're also going to draw a distance from the edge, or from, we call this the axis of revolution. Let me backtrack a little bit here. We're going to take this region and rotate it around the x-axis. What shape do you see if we were to separate the resulting object into thin slices? We see these circular discs. So from the axis of revolution to the edge of the boundary, we're going to also draw this length, but this length is no longer going to represent the height of rectangles. This length is now going to represent the radius of these circular discs. Obviously, all these extremely thin discs, circular discs, all have different sizes. And so we can expect each of them to have a different radius. Same thing here, right? This is just one representative height of a rectangle. All the heights are different. This is just one representative radius of the circular discs. All of them are going to be different. So let's just take one thin slice of the circular disc and just talk about what we can build that example, and then we can accumulate it using integral. So the face of this circular disc has an area of pi r squared. So the area of this circular disc is pi r squared. But we're going to call this r of x, which represents radius. We purposely are doing this uppercase r because later on we're going to have something called washer method, where we're going to subtract a hole out of the object. So that's going to be represented by a lowercase r. So right now we're going to use uppercase r to represent that radius of this circular disc. So my area can be built as pi big R of x squared. Now, area is a two-dimensional calculation. And then this infinitely thin width of this disk, we're going to call it dx. So if I have area and a width component, that will give me that third dimension, right? Area is already two-dimensional. That dx will give it that third dimension. And now we're going to add up these infinitely thin circular disks from one end to the other. And so my volume formula is the depth integral from x sub 1 to x sub 2 pi big R squared dx. Notice how before with our area formula is just height and width, right? That's one dimensional times one dimensional, we get two dimensions, but this one has three dimensions to it because area is already two-dimensional and we're adding that width component. So two-dimensional, one-dimensional, we get three-dimensional, and then we're accumulating all these disks from one end to the other. Okay. Now the nice thing is that once we have the formula built, we just dump into the formula and make the calculus do all the work for us. We don't have to worry about, oh, I got to figure out all these different heights and got to add up all these different radius and all these different areas. It's really, once we have the formula in place, the rest can just be plugged into the formula, just like how we did here, right? With area, once we have the formula set, then the rest can just go in the calculator. Okay, so now that I've kind of gone through an example, we're going to actually work out this problem. So we're going to actually find the volume of this particular bowl or this this object. So example 1, find the volume of the solid formed by rotating this curve y equals root x around the x-axis between 0 and 4. So, this is a three-dimensional representation of what the object looks like, but it's just, we're always going to draw it two-dimensionally. And as long as we can get all the parts, we can just put it into the formula. So we don't have to draw it exactly like like a three-dimensional object. So same idea, right? We have root x, we have the x-axis, we have bounds from 0 to 4. So here's our shaded region. And we're rotating around the x-axis. So this is our axis of revolution, which I'm going to abbreviate as AOR, axis of revolution. So I'm always going to use dotted lines here. So your dotted line is the new center of your object. It's always going to look like it's at the edge, but after rotation, it's always going to end up being in the center of the object. So we have rotation of the object. Now, the way you build your radius is always going to be perpendicular to your axis. So whichever direction your axis is going, you're always going to go in the opposite, not opposite, but you're always going to go in the perpendicular direction as your axis. So because my axis is horizontal, my radius has to be vertical. Okay. Next page, we're going to see a vertical axis, which means our radius will be horizontal. So these will always they'll always be at a 90-degree angle with each other, right? Your axis and your radius. Okay. All right, let's build our radius. We have root x, we have 0, and then our big R, big radius, big R of x, is simply top minus bottom. The calculation that we're going to build is much the same way as top minus bottom for area. It's just now it represents something a little different, but it's going to look the same in terms of the diagram that we're pulling. So root x minus 0, top minus bottom. Our bounds is from 0 to 4. You're going to find bounds the same way as area. Okay. You're just going to find the bounds of your shaded region. Sometimes your axis is going to be far off the grid, and we don't care about where the axis is. We only care about the shaded region. So your bounds is just for your shaded region. Okay, so we're just going to follow this top minus bottom, this vertical radius formula here. So pi and then x of 1, x of 2. Typically, now we see pi r squared here, but typically because pi is a coefficient, we typically pull the pi out in front and then put the radius out here. It's not wrong if you put the pi inside the integral. It's just typically, we'd like to have that here as a reminder that when we plug in the calculator, we typically don't plug the pi in the calculator. We just let the calculator find the numeric approximation, and then we attach pi at the end. That's typically how we're going to do things. So we're going to go from the furthest left to furthest right of the shaded region. So the furthest left is 0, furthest right is 4. You know, virtually the same identical setup as area. It's just that instead of height is now radius. So from 0 to 4, we know the radius is simply root x. So we're going to do root x quantity squared dx. So this is my area formula here built into it, pi r squared. Eventually, we're going to put this in the calculator, but I think this is easy enough to do by hand. Integral of x dx, because the root x and the squared will cancel out. X just becomes x squared over 2. And then upper and lower bound, we get 4 squared over 2 minus 0. 16 over 2 is 8. Now we have 8 as the calculation, but don't forget about the pi. We're adding infinitely thin circular disks, so pi is always going to make its way into our formula. So 8 pi, it's three-dimensional calculation volume, so cubic units. This is the volume of whatever this object shape turns out to be. Okay, next page. Okay, example 2, we'll do another top minus bottom, and then the harder ones are the right minus left, but we'll do another top minus bottom here. It says find the volume of the solid created by f of x equals 2 minus x squared. And, sorry, I forgot to put this other boundary here, and y equals 1, about the line y equals 1. So I need to show you the boundary first, and then tell you the axis of revolution. So the axis should be different than, I mean, it should be a different statement than the boundary of the shaded region. All right, so this is what our graph looks like. 2 minus x squared is a parabola that opens down because it's a negative, and the 2 is indicating that y-intercept. So we have parabola that opens down, and it's cut off by y equals 1. So y equals 1 is a horizontal line. So here's our shaded region. So it kind of looks like a dome-shaped object here. All right, we're going to rotate this shaded region about the line y equals 1. So this is our axis of revolution. And we're never going to be drawing these three-dimensional objects. We just have to kind of visualize what it is. So if you can kind of visualize, okay, after I take that, and if I rotate it, it's going to kind of create like an egg-shaped object. So one important thing that we're going to need to do on this problem is that the intersection is going to act as the bound. So we're going to have to find the intersection, because the intersection will help us find that x sub 1 and x sub 2 that we need. So let's find the intersection here. So we find intersections by setting the equations equal to each other. So I can say 1 is equal to 2 minus x squared. I'll bring the x squared over so I can have that being positive. X squared is equal to 2 minus 1, which is 1. Take the square root, I get plus or minus square root of 1, which is plus or minus 1. So we know we're starting at -1 and we're ending at +1. Let's draw our representative radius. Your radius is always going to start on the dotted line, and it's going to extend to the boundary. So we're always going to put our pen or pencil directly on the dotted line first, and from the dotted line, extend to the furthest boundary. Okay, it doesn't matter where you draw your radius. It could be here, it could be over here, but as long as it's a vertical radius, that's what we want. We want a vertical radius somewhere in that diagram. It kind of helps us get our bearings for this problem. So let's build our radius. Our radius is a vertical radius. So if I have a vertical radius, I'm going to do a top minus bottom formula, because it's also a horizontal axis of revolution. So a horizontal axis, vertical radius, I'm going to use this formula. Right. So big R, big radius. Again, we haven't talked about little radius yet. That'll be on Friday. But right now, this is acting as the only radius. So I'm going to call it uppercase R. So top minus bottom, the top of the radius is sitting on that curve, and that curve is what is 2 minus x squared. So 2 minus x squared, that's my top boundary, minus my bottom boundary. My bottom is sitting on that horizontal line, which is at y equals 1. So top minus bottom is 2 minus x squared minus 1. Clean that up, I get r of x is 1 minus x squared. Okay, I think we have everything that we need to put into our formula. So v is equal to pi comes first, x sub 1 to x sub 2. So -1 to 1, we have our boundaries from -1 to 1. We have our radius built, so just put our radius in. And we got to square that, right? Pi r squared. Pi r squared. Hey, we could work this out by hand, but we'll have to go through, expand this out, go through power rule. But let's just practice putting this in our calculator, since ultimately on the quiz, this is what you're going to be doing. You're going to set it up, and then just the rest goes in your calculator. So this is what I like to do. I like to store my radius. I like to store the radius under y1. For future purposes, it just means that less parentheses gets in the way, and it's just a little bit cleaner. It's not wrong if you want to put everything into your Math 9 line, but I like to split it up. So under y1, I'm going to have my radius being 1 minus x squared. Go back to your home screen. Now do Math 9. Now, as you put this into your calculator, don't put pi in the calculator. If you put pi in the calculator, I mean, it'll still give you an answer, but it'll give you like a decimal version of the answer. And if we just put this integral in without pi, we may have a chance to have an exact value rather than having, because if you put pi in the calculator, it'll return you a decimal value. It won't return you pi, the notation pi. So typically I like to have that flexibility to be able to present the exact answer without it being a decimal version. So now sometimes without the pi, it may still not give you a full exact value, but at least there's a chance. Okay, but if you put pi in, we have no chance of getting that exact value. So Math 9, we're leaving pi out of the calculator. We're going from -1 to 1. I'll do alpha trace y1 because I have y1 holding my radius. And the nice thing is we don't need a set of parentheses. We can just do squared. Whatever is stored under y1, we don't have to put parentheses squared. We can just do y sub 1 squared, and it's going to square everything inside the radius. And make sure you close that off with dx. If you do math fraction, see if it'll convert that to a fractional value. It does. So our volume is 16 over 15, but don't forget there's that pi there as well. So 16/15 pi units cubed. Anytime that there is a rotation going on, the fact that the rotation is occurring, it's always going to create these circular shapes. So pi is always going to be involved whenever we have this rotation, this volume by rotation. Hey, any questions? Okay, example 3. These are more challenging because our radius is going to end up having a different orientation, which means that our equation has to be rewritten. Our bounds has to be adjusted, and it's just I think the right minus left is always going to feel more challenging because there's just more things that we need to do to get things set up. All right, given the region formed by the function x-axis, so you got x-axis, you got the y-axis, and then you have y equals -x plus 1. That's this linear graph, and it's going to create this triangle here. And we're going to take this shader region, and we're going to rotate this region around the y-axis. So my axis of revolution is now going to be x equals 0. So let's do a dotted line. I like to use a different color here. And if you can imagine, after this shape gets rotated around, it's going to kind of create like an upside down cone. Okay. Again, it's not the end of the world if you can't visualize this. As long as you can set up your diagram and get your bounds and your radius, then really that's all you need. But I just want to kind of help you see that the idea is that after this rotation goes on, it kind of has this upside down ice cream cone looking shape. So from your dotted line, you're going to extend from your dotted line to the edge of your boundary. And again, this looks like the edge of the diagram, but after everything is said and done, we know this is really the center of the diagram, right? This is really the center after the rotation occurs. And because the axis is vertical, our radius is going to be horizontal. So you're always going to have this 90-degree relationship or this perpendicular relationship between your axis and your radius. So it doesn't matter where you draw the radius as long as you can just have, I typically like to pick somewhere in the middle to draw, but if you put it down here, it's fine. Put it up here, it's fine. Now, what is challenging about these horizontal radius, this horizontal length, is your equation is typically not going to be in the form that it needs to be. So anytime we see a horizontal radius, a horizontal length, our equations need to be written in a different form, meaning that these have to be in the form of x equals. Okay, for top minus bottom, these are nice because everything is ready to go. Y equals this, y equals that, and we can just plug in. But these equations have to be x equals so that everything on the right is in terms of y. So I need to spend the time to actually rearrange this equation and get x by itself. So if I solve for x, x is equal to 1 minus y. So now this equation represents this linear graph that we see in front of us. It's in the better form for us to put into our formula. The other equation that we're going to need is this y-axis, and y-axis also has the form of x equals. It's x equals 0. So if you see x equals, you know the right side is ready for you to put into a right minus left formula. Our bounds are also different as well. Our bounds, we're not going to go from left to right. We're going to go from bottom to top. We're going to find the lowest y value, and we're going to go to the top y value. So imagine this. We're adding infinitely thin circular disks from this end of the diagram to the top end of the diagram. And we see that the lowest y value is 0, and the highest y value is indicated here at 1. If 1 wasn't provided for you, you could plug 0 in for x and get the y-intercept, which is y equals 1. Okay. All right, let's build our radius. Now our radius is horizontal, so we're going to say r of y, not r of x, r of y. All right, right minus left. So we look at what is the right boundary of our shaded region. It's going to be the 1 minus y. We're going to look at the left boundary of the shaded region, which is going to be 0. So it's going to be right minus left. This is my right. This is my left. 1 minus 0 is my right. 0 is my left. And so just being 1 minus y. Right, so now we're ready to put into our volume formula. Pi comes first, integral from lowest y value to highest y value. So from 0 to 1, and then big radius, quantity squared, dy. This is what I want to see on paper, but in your calculator, you're going to use what variable? X, yeah. So I'm going to have y1 hold my radius. And I like to just wait for the square to come later. That way I don't have to use as many parentheses. So I'm just putting my radius in, and then I'll save the squared for when I enter in the calculator. So I have 1 minus x under y1. Go back to your home screen, math 9, from 0 to 1. Again, leave pi out of your calculator. I'll do alpha trace y1, then I'll square it, and then dx. .333, if I do math fraction, it gets me to 1/3. So don't forget about the pi. So my volume is 1/3 pi, or pi over 3 units cubed. All right, part B. We're also rotating around the y-axis. So here's our shaded region. Axis of revolution is vertical, which means my radius has to be in a different direction. It has to be horizontal. And we're picking our formula based off of the orientation of our radius. If our radius is vertical, then we know it's an easier problem, which is top minus bottom. No need to change our equations. But anytime we see right minus left or horizontal radius, we know the equation has to be rewritten, needs to be adjusted, needs to be solved for a different variable. So we're going to go ahead and rearrange this equation. I'm going to solve for x because right minus left, everything has to be in terms of y on the right side. So let's say x squared is equal to 4 minus y. I'm just rearranging it, trying to get that x squared to be positive. And then I still need to take the square root to get that x by itself. So x equals plus or minus square root of 4 minus y. I can't break this any further because there's a subtraction inside. I got to leave all that inside the square root. But I'm going to choose the positive square root. The negative square root is going to be in the second quadrant, which is not part of our diagram. So the curve is just going to be x equals positive square root 4 minus y. The left boundary is, again, the y-axis, which is x equals 0. Our bounds, what are our bounds going to be? Is it from 0 to 2? What should our bounds be? From 0 to what? Okay. We're not picking the x values from left to right. We're picking the y values from bottom to top. What's the lowest y value? 0, right? What's the highest y value of the shaded region? 4, yeah. So we got to go from 0 to 4, not from 0 to 2. If we do 0 to 2, that will be good for top minus bottom, but not for right minus left. So everything has to be in terms of y. Our equation is in terms of y. Our bounds are also in terms of y. Okay, let's build a radius. Sorry, so r of y is right minus left. The right boundary of my shaded region is the root 4 minus y. The left boundary of the shaded region is sitting as that x equals 0. I can drop the 0. Sorry, I can drop the 0. Just root 4 minus y. Okay, ready to put into our volume formula. Pi comes first, integral from 0 to 4, big radius, quantity squared, dy. Okay, let's practice plugging the calculator. I got 8. Don't forget about the pi. So 8 pi units. Right, let's see if we can squeeze in another practice problem here. Let's go to page 11. Let the region R be the area enclosed by y equals 2x cubed. That's going to be the cubic function that you see here. Line y equals 8. That's the horizontal line up here. And the y-axis. So go ahead and shade in that region so you know what to focus on. We're rotating about the line y equals 8. So this is my axis of revolution. Put that dotted line right at y equals 8. This is now the true center of our object. This object is going to get rotated upward like this, it's going to end up like looking like a sideways shallow bowl object. And once you have your axis, you can draw your radius. Your radius is always perpendicular. So in this case, our radius is going to be vertical. And because we see a vertical radius, we know we can do top minus bottom. This should be an easier setup. No need to rearrange equations. Our equations are typically going to be ready for us to use. Oh, let's go ahead and find the boundaries here, because the bounds is as far left as 0 and as far right as this intersection. So we do need to find this intersection so that we can figure out what that right boundary of the shaded region is. So go ahead and set up your intersection equation. So this is the intersection of the cubic function and the y equals 8. So we'll just set these equal to each other and solve for x. I ended up not having a nice integer value, but cube root of 4 is where that right endpoint of the shaded region. So we'll need to use that when we get to our integral. All right, let's build our radius, top minus bottom. The top of the radius, sorry, the top boundary of the shaded region is the y equals 8. The bottom of the shaded region is the 2x cubed. So that 8 minus 2x cubed will keep adjusting and changing and adjusting to all the different heights of length of the radius from one end to the other. All right, we're ready to put our formula together. Pi, definite integral, x sub 1 to x sub 2. Furthest left is 0. The furthest right is cube root of 4. And then big radius squared. Okay, put into your calculator. If you want to do cube root of 4, you're going to do math 4. I think math 4 will get you that cube root notation to show up. But you can have the 8 minus 2x cubed in your y1. So this one ends up giving me a really messy fraction. If that's the case, just do a decimal version of the answer. So if you do a decimal version, then round it to 3 decimal places and then attach pi at the end. Okay. Any questions? Okay, your homework. Your homework is page 1 and 2 in the homework packet that you just picked up. I'll send out a reminder tomorrow. This will be due on Friday, and then I'll also send you a link to the key where you can check your answers. So this method, just pages 1. As you guys come up, if you want to pick up the formulas quiz that you'll be working toward for next Wednesday, you can pick one up here. I have a practice sheets as well as the key attached. So, and I can give you more practice sheets next week if you want to have more practice. Okay, come get your phones. If you don't pick up the practice sheet, it's okay. I'll give it to you on Friday.
Right? I mean, yeah. I love it. It makes me excited. I realized yesterday, I think I leaned in. Like it's just something that plus I should it's a lot easier.